So we have two players with inputs x and y, and they're interested in computing some joint function f of x and y. F can be, for example, the equality function, does x equals to y, or maybe if we think about x and y as two numbers, whether x is greater than y. So they exchange some bits until the center observes this exchange, has enough information, and can output the value of f at x and y. Okay, so we're going to do the usual. We're going to use the standard definitions. We're thinking about a communication protocol. So the communication, so CCP is going to be the number of bits that is exchanged in the worst case by a protocol P that can always decide f. Okay, can always determine whether x equals to y, x is greater than y, and so on. And the communication complexity of f, of a function f, is the communication complexity of the best protocol that always correctly computes f. So this is actually the minimal number of bits that we need to determine f. Okay. Now, arguably, what we do in communication complexity, in researching communication complexity, is like, you give me a function f, and I want to tell you how many bits we need in order to compute f. We're going to do exactly that in this talk, but we're going to do that for a certain interesting class of functions, though that represent mechanisms. So we're going to think about the two players as having some private information. This is their valuation for every possible alternative. They're going to exchange some bit until the center has enough information in order to output the alternative, for example, the allocation of the items and the associated payments, who pays what. Okay? So this is basically what we want to do. So a mechanism is simply a function that takes as input takes the valuations as input and outputs the alternative and the payments. And we will look at mechanisms that are incentive compatible in the sense that each player has a dominant strategy, one that always maximizes his own profit. Okay? So this is what we want to do. And the communication complexity of a mechanism is simply the minimal number of bits that we need in order to compute a certain compute the output and the associated payments. That's what we do. And the goal of this talk, you give me an incentive-compatible mechanism A, and I have to tell you how many bits do we need in order to implement this mechanism. Okay? So that's what you want to do. Now, the issue is that working directly with this dominant strategy mechanism is not that easy. And it's actually going to be easier to work with an alternative, an equivalent interpretation of these mechanisms. And we're going to use the well-known taxation principle for that. And the taxation principle tells us that if we have an incentive-compatible mechanism, we can think about it in the following way. Each player I is presented with a menu. A menu is just, a price for each possible alternative. Okay? This is a menu. This menu depends, the menus that player I sees, the price for each alternative, depends only on the valuations of the other bidders. Okay? And like the magic in truthful mechanism, in incentive-compatible mechanism, is that each player sees like a list of prices that does not depend on his own valuation, but only on the valuations of the others. But each player chooses the alternatives that maximizes his own profit. But somehow all the players simultaneously agree on the same alternative. So the same alternative maximizes the profit of all players. Okay? So each player just sees a list of prices, one for each alternative that does not depend on him. He simply chooses the one that maximizes his own individual profit, and somehow they all agree on the same alternative. Okay? So this is one interpretation of incentive-compatible mechanisms. Let's do a very simple example. Suppose we have a second price auction. We have two values, V1 and V2. We only have two players here. What is the menu that is presented for player 2? The first alternative is player 2 gets the item. The second one is the other player, player 1 gets the item. If the chosen alternative is player 2 gets the item, then player 1 pays V1, the value of the other. Otherwise, he pays 0. Okay? And the other bidder has a similar menu. Okay? And they both choose the same menu. If, for example, V2 is greater than V1, both will choose player 2 gets the item and will pay different prices. And so every incentive compatible mechanism can be interpreted like that. OK, so now that we have this menu-based thinking of truthful mechanisms, we can go to maybe the most important definition of this talk, which is the taxation complexity. So the taxation complexity of an incentive compatible mechanism is simply the number of bits that you need in order to represent an index of a menu in the mechanism. Okay? A little bit more formally, let's just isolate some bidder I, and let's vary the valuations of all other bidders and just count the number of menus that this bidder might see. Recall that the menus that a bidder is presented with depends only on the valuations of the others. So count the number of menus that a player might see, okay? And the number of bits that we need to represent an index of a menu from that menu is simply log the number of this set, the log of the size of this set. Okay, and we take the maximum over all players.
So why is this called taxation?
Why this is called taxation? Okay, because it actually came from an actual book about theoretical understanding of taxation. So this is like you tax every possible alternative, and you do whatever is best for you. And now we see what everyone is doing. So that was the original motivation. Okay. OK, so I just want to make sure that we all understand that we only in this definition, we only care about the number of menus that a player might see. We don't care about the complexity of each single menu. We don't care about the price of every single number of finite entries, whatever. We just count the number of menus that the players might see and take a log. That's all. This is taxation complexity.
Just to make sure,
yeah.
The last example, this is 2.
In the second price auction example, this is 2. Yeah. If you have 2 players, this is 2. Good. OK.
You have different menu for each price of the first player.
What?
Depends on the number of different prices.
Sorry, yeah. So, yeah. Thanks. OK. The number of alternatives in the menu that you have is 2. And for, we just take, if you have 100 values for each player, then, do the calculation and take a log of that number. OK? Thanks. OK. So this is the taxation complexity of the mechanism. And now the theorem, the informal theorem, says that the taxation complexity is essentially equivalent to the communication complexity. That is, if you want to understand the communication complexity of a mechanism, then just count the number of menus that a player might see and take a log. Okay? Now, you might think that this statement is trivial. I'll try to convince you that it is. Then we'll see that it's not that trivial. And then we'll see why it's actually not true at all. So let's start with understanding why this statement is trivial. Well, we know that each player just has to choose the profit maximizing alternative. He sees a bunch of prices and just takes the profit maximizing alternative. Okay. Of course. So what can you do if you want to choose your profit maximizing alternative? You must know the full menu, and in order to transmit the menu, you must send the index of that menu, at least this index of this menu. This is like, from basic information theoretic arguments. But this is not really true because we have 2 players that are interacting between them. And maybe they can save some bits of information. You don't have to learn the full menu. You just have to find the profit maximizing alternative. So that's like 2 different things. So interaction, we know that interaction might help in order to save bits of information. OK.
So one direction is always true?
So we'll see that. OK. So what I want to show you next is that actually a counterexample to this theorem, a situation where the taxation complexity is not even close to being the communication complexity. But this counterexample will help us, exactly understand when this theorem is true and when it's not. OK, so let's start. So what is the example? So it claims that there exists an incentive-compatible mechanism A for which the taxation complexity is not only that it's not about the communication complexity, it's actually exponential in the communication complexity. Okay. The proof of this theorem is 2 lines if you know the right terms. This is simply VCG applied to combinatorial auctions when the valuations are gross substitutes. And what I'm going to do in the next 2 slides is we're going to understand each of these terms and see why they imply the claim. OK, so let's think about a situation, the standard model of combinatorial auctions, where we have n players and m heterogeneous items. And each player I has some value for each subset of the items. The output, the set of possible alternatives, is simply a partition of the items. Okay. What are gross substitute valuations? These are some subsets of valuations. The exact definition is not really important for this talk. Intuitively, this is just the largest class for which a Rayleigh equilibrium always exists. So this is a rich class, a nice class, important class. Exact definition is not really important for this talk. OK. What is really nice about gross substitute valuations is that if you have a gross combinatorial auction with gross substitutes, is that you have fast algorithms that compute the optimal allocation. Okay. There are a number of ways to do that. There is a natural ascending auction process that does that. Linear programming-based approach, graph theoretic algorithms. Many ways, all of them terminate in polynomial time, and in particular imply polynomial communication. Once you can efficiently compute the optimal allocation, you can also compute VCG prices. And we get that the communication complexity of VCG is polynomial in m and n, the number of items and the number of bidders. Good. So that's a small communication. What about the taxation complexity? Let's consider VCG for 2 players. And let's fix 1 player with valuation V. What is the price of bundle S in the menu that V is presenting to the other? Okay. How much a player will pay if he takes the bundle S? Well, it will pay his damage to society, which is the value of the grand bundle minus the value of the complement of S. Okay. Immediately from the definition of VCG. So what we get is that if you have a valuation V and you present to the other players some menu, there is a 1-to-1 correspondence between the bundle S and the price of bundle S and the value of the complement of S. Okay? That is, every menu uniquely defines a valuation and vice versa. Okay? This gives us that the number of menus that a player can see is exactly the number of possible valuations, the number of possible Vs. Okay. So all I have to show you is that the number of valuations is high, if the valuations, even if the valuations are restricted to be gross substitutes. Okay. Fortunately, we don't have to calculate this. Knus has already done that for us. The number of gross substitute valuations on m items, even if you restrict yourself to integers between 1 and m, is something that is doubly exponential in m. So the taxation complexity of VCG is the log of something that is doubly exponential. That is, the taxation complexity is exponential in m and n. Okay? So we have a situation where the taxation complexity is very high, but the communication complexity is small. Okay? Okay, good. So what is actually the relation between the taxation complexity and the communication complexity? Here is the first relation. We can prove that if the valuations are not restricted, not just general, not just gross substitutes or something like that, if they are general, then the taxation complexity is at most the communication complexity. If you're interested in more restricted classes like subadditive or submodular or stuff like that, we also have like similar theorems. But if your domain of valuation is rich enough, then the taxation complexity is always bounded from above by the communication complexity. Okay. Proof of this is not that easy. I don't think I will have time today to show you this theorem. But what I do want to show you is how to prove the other direction, which essentially says that the communication complexity is at most the taxation complexity. OK. So let's focus for a second on the case where we have only mechanisms for 2 players. Okay. And I want to sort of claim that the communication complexity of A is 2 times the taxation plus some additional polynomial factor. Okay. This is not going to work, but here's like here's the idea. We have 2 players. And we know that the menus that the player sees depends only on the valuation of the other. Okay? What does it mean? It means that each player can internally look at his own valuation and with no additional communication cost can compute the menu that he presents to the other player and simply send text A bits that represent the menu that he is presenting the other player with. Good. So each of the players does that. That's 2 times text A bits. And now each player has the menu. So what's more obvious than just choosing the profit maximizing bundle? Okay. That's exactly the part that doesn't work because in principle there might be several bundles several alternatives that maximize the profit, and we have to do some tie breaking between them. Okay. So we somehow have to account also for this tie breaking. So let's define the tie breaking complexity of a mechanism as the communication complexity of choosing the right profit maximizing alternative, but given that we have the menus. Okay, so we have the menus, and now each player knows what is the set of profit maximizing alternatives, and now we just have to decide which alternative is actually being chosen. If we have this, then we get that the communication complexity of A is at most 2 times the taxation complexity plus 2 times the tie-breaking complexity. And notice that we also have that the tie-breaking complexity is almost at most the communication complexity of a mechanism. Just run the mechanism and see what output do you get. Okay. So once we have this, we can characterize the communication complexity of every 2-player mechanism. Before I told you that the taxation complexity is at most the communication complexity, and this shows that the tie-breaking complexity is at most the communication complexity, so the average is also at most the communication complexity. And for the other side, we have this protocol that gives us the communication complexity, an upper bound on the communication complexity. So we're able to characterize the communication complexity of every 2-player mechanism up to a factor of 4. Okay. Now, I sort of want to claim now that the really important term here is the taxation complexity and not the tie-breaking complexity. And there are 2 reasons for that. Okay, so one is that I actually know of no mechanism like in the wild in which the tie-breaking complexity is high. Sure, I can develop contrived artificial mechanisms in which the tie-breaking complexity is high and the taxation complexity is low, but that usually is not the case in every mechanism that I know. The other way of the other argument for claiming that taxation complexity is more important is by looking at the smooth communication complexity of auctions. Take a set of valuations and just add some random noise to them. We really don't expect to have more than 1 profit maximizing alternative with high probability. Okay, so the tie-breaking complexity is not really important. And this means that the taxation complexity characterizes the smooth communication complexity of every truthful mechanism up to a factor of 2. Okay. Okay. This was true for 2-player mechanisms. What about n players or more? The part that doesn't work here is this thing. It is no longer true that each player can internally look at his own valuation and compute the menus that he's presenting to the other guy, because this menu might depend on the n-1 other players. They might need some interaction in order to compute it, and the question is how much interaction do they need? The answer is not too much. That determining the menu that is presented to the other player can be done in time that is polynomially the taxation complexity, m and n, and something that is called price A. Price A is simply the communication complexity of computing a single price in the menu. So if you can tell me for every player I in bundle S, what is the price of I in the menu that the other player are presenting to S, with just really few queries like this, I can compute the old menu that is presented to every player. So our full protocol, so we can have the final characterization for n-player mechanism. It's easy to see that the communication complexity of price A is at most the communication complexity of the mechanism, so the average is also at most the communication complexity of A. And for the other side, we just compute for every player the menus that he is presented with, break ties, and that's it. Okay, questions? Okay. So this characterizes the communication complexity of every mechanism. And similarly, we can claim that the really important term here is actually the taxation complexity. OK, some applications and extensions. Actually, let's just do that. We can also extend our result to value queries. So up until now, we just discussed a general model where each player just send whatever he wants, just the general communication model where each player sends a few bits here, a few bits there, and they exchange whatever they want, and until they reach a conclusion. It is quite popular to restrict the access to the evaluations, in particular via value queries. Given a bundle S, what is the value of S? And here we can define a term that is called the menu complexity as the maximum number of entries in any menu that is presented in the mechanism A. This was already used in several papers before in a slightly different context. And we get that the menu complexity characterizes the number of value queries that a mechanism must make exactly in the same way that the taxation complexity characterizes the communication complexity. So the expression is the same, proofs are really not. Okay. Okay. Another application is that this taxation-based thinking about mechanisms gives us two possible new approaches of proving one of the holy grails in algorithmic mechanism design, which is proving some gap between the power of incentive compatible approximation mechanisms and non-incentive compatible approximation mechanisms all run in polynomial time. Let's do that via an example, but the situation is really the same for almost every problem that we care about in algorithmic mechanism design. So let's think about combinatorial auction, and now let's restrict our bidders to have some modular evaluations. And we know that there is a 1.57 approximation to the welfare that runs into polynomial time and uses polynomial communication. Okay. This is quite a good ratio, but the best incentive compatible mechanisms that we know guarantees only a poor approximation ratio of square root of m. Okay, so we really have a large gap, and we have no idea which is the correct answer, 1.57 or square root of m. Okay, we have no tools in order to prove any gap between the two, and the situation is really similar for many other problems. Okay, so we know some impossibilities, but this is only for the special case of value queries, not in the general communication model. So how can we prove impossibilities for such a problem? Here is one possible approach. We can show that if you have a two-player alpha approximation algorithm that is also incentive compatible, there is also a two-player alpha approximation mechanism algorithm that uses simultaneous communication with the same communication. So what is a simultaneous algorithm? Simultaneous algorithm is one in which the two players speak simultaneously without knowing anything about the evaluation of the other. They both send, like, say, polynomial messages, and the center can give us the best, can give us a good allocation. So what the theorem is saying, that if you have an incentive-compatible mechanism, you also have a simultaneous algorithm, one that does not need interaction between the players. So if we want to prove some gap, if we want to prove that incentive-compatible mechanisms can do something, can guarantee a good approximation, you only have to prove or disprove that no simultaneous algorithm with polynomial communication for two players can achieve an approximation ratio of 1.58. If no simultaneous algorithm can achieve an approximation ratio of 1.58, this means that there is no incentive-compatible two-player algorithm, maybe even interactive, that achieves this ratio. Okay, so this is all you have to show. We actually, so we have many strong bounds on the power of simultaneous algorithms, but unfortunately they hold for many players. For two players, we really don't know much, and there is recent progress in on this question by Braverman et al., but we still don't know the answer for that. Okay, the other approach is a little bit more direct. just prove that the taxation complexity of any incentive compatible mechanisms that guarantees an approximation ratio of 1.58 is exponential. This is enough. Why? Because we know that the taxation complexity is a lower bounded communication complexity. So if we prove a lower bounded taxation complexity of an incentive compatible mechanism, this gives you immediately a lower bounded communication complexity. And notice that here we don't say anything about polynomial time. Just prove that if you have an incentive compatible mechanism that guarantees a good approximation ratio, then its taxation complexity is really high. Okay. Okay. I think I skipped the proof that the taxation complexity is a lower bounded communication complexity. Okay. So to summarize, what we did in this talk is to characterize the communication complexity of truthful mechanisms. And we basically showed that if your domain is rich enough, then the taxation complexity is essentially the communication complexity. That's like the more interesting term that we have. Okay? Thanks. Questions?